Welcome to qnawire.
In this problem, we're going to talk about rotational kinetic energy. So consider that we have an object that's rotating. So this is a rigid object that's rotating. The object has a moment of inertia I, a mass m, and a radius r, and is rotating with um, with an angular velocity omega. Then the rotational kinetic energy of that object is 1/2 of the moment of inertia times the angular velocity squared. This is the kinetic energy due to rotation. And if the center of mass also has a velocity, then the kinetic energy of the center of mass is 1/2 of the mass v squared. Okay. Um, so now we can go on to our exercise. So consider that we have a track as shown here in the picture. Sorry, let me do it a little better. Okay, this is the track. It has a height h0. The radius of the loop here is r, and these points are called A and B. And we have a small hollow sphere that has a mass m and a radius r, and it starts to roll down from rest, and it rolls without slipping downhill, and we want the sphere to make a loop, to complete the loop. So basically, what we want to do is to find what is the minimum value of h0 such that the loop will be completed. Okay, so the first thing we need to notice is that when the particle is in the loop, in order for it to reach point A, uh, the minimum value of the normal force must be 0. Okay? Basically, there's a normal force that the track exerts on the object, that's downwards, and also downwards we have the gravitational force. So the total force is equal to the normal force plus the gravitational force, and the minimum value of the normal force must be 0 so that the object uh, can still be on the track but on the verge of falling off. So basically we want the force to be at least equal to mg. Okay, so we want, and since the force is equal to the centripetal acceleration times the mass, then we want v to be equal to the square root of g times r. So we want the velocity of the object at point A to be equal to at least the square root of gr. So initially, the initial energy of the object is mgh0, and the final energy is the gravitational potential energy at this point, which is equal to 2 mgr plus the uh, the kinetic energy of the center of mass, that's mv squared, plus the kinetic energy, the rotational kinetic energy, that's 1/2 of I omega squared. Now, the first thing we need to notice is that the moment of inertia of a hollow cylinder is, sorry, a hollow sphere is 2/3 of m r squared. We also need to notice that for the motion to be rolling without slipping, then v must be equal to omega r. Okay, so we have that. I'm going to cancel, actually, before canceling anything, let me write this as mgh0 is equal to 2mgr plus 1/2 of mv squared plus 1/2 of 2/3 of mr squared times omega squared, and omega squared is v squared over r squared. The m's have to be cancelled. Okay, and now I'm going to use that V is equal to the square root of GR. So GH0 is 2GR plus, notice that we have 1/2 plus 1/3 of, um, actually, I'm sorry, up here, V should be equal to omega lowercase r, not omega capital R. I'm sorry for that. Okay, so the r's cancel out as well. So we have 1/2 of V squared plus 1/3 of V squared. So that's I'm sorry, 5/6 of V squared. So H0 is 2R plus 5 times V squared, that's GR, divided by 6 G. And this is equal to 17R over 6. This is the value of H0. Then in question B, we have to find how hard, what is the force that the track exerts on the object at point B. Point B is this one here. So notice that the horizontal force, that is the normal force, is responsible for the centrifugal acceleration. So the normal force will be mv squared over r. Um, so what we need to do is remember that the initial uh, gravitational potential force, I'm sorry, is mgh0. The final one is mgr, since the height here is just r, plus uh, 1/2 of mv squared plus 1/3 of mv squared. The second term comes from the rotational kinetic energy. So in the end, it's just 5/6 I'm sorry, 5/6 of mv squared. And v, in this case, we can find the value of v. So v is equal to 6/5, the square root of 6/5 of g h0 minus r. Now h0 is 17 sixths of r. So h0 minus r is 11 sixths of r. Meaning that v is the square root of 11/5 gr. So the normal force is equal to m v squared divided by r. So this is just 11 mg over 5. Okay. Then in question C, we have to suppose that there were no friction along the track, meaning that the object would roll while sleeping, meaning that omega would be 0. There would be just the center of mass velocity. And our goal is to find, in this case, if it would be enough, the height that we found back in question A of 17r over 6 would be enough for the object to complete a loop. Well, notice that in this case, we have that the initial kinetic energy is the same. I'm sorry, the initial potential energy is the same. And the final kinetic energy is just the center of mass kinetic energy. Since before we had an additional term, then this is smaller than the original kinetic energy, the original total kinetic energy. So there's enough gravitational potential energy in the beginning to to give the system the necessary kinetic energy of the center of mass at point A. So the answer is yes. There would that would be enough. Okay. Then in question D, we have to find, considering that the object slips while rolling, we have to find what is the normal force that the track exerts on the object at point A, so up here. Well, notice that the normal force plus the gravitational force is equal to mv squared over r. And also, we need to find the value of v at that point. So I'm going to use the conservation of energy. So I have 17 mgr over 6. This is the initial potential energy. The final potential energy is 2 mgr. And the final kinetic energy is just 1/2 of mv squared. Now writing 2 as 12/6. Then this is, then we have 5/6 of mgr is 1/2 of mv squared. So v is equal to the square root of 5/3 of gr. Okay, so the normal force is v squared over r minus g. Now v squared over r is 5g over 3. So this is 2/3 of g. And we have to compare this with the normal force that is exerted on the object when when the object rolls without slipping. In that case, remember that we assumed that n would be equal to 0. It's up here. Okay, because we wanted the minimum value of h0. So in that case, in the case of question A, n would be equal to 0. And this concludes our exercise.